Hello everyone. So in today's video we are going to go over this old paper by David Yarowski on unsupervised word sense disambiguation, rivaling supervised methods. So this is the first paper mentioned in this GitHub repository, which mentions papers for data augmentation techniques in natural language processing. So I'll try to cover all the ones which I find relevant for my work, and I also wish to share with others. So this is the first time I'm reading this as well, but hopefully we can make sense of this paper together. So the abstract, this paper presents an unsupervised learning algorithm for sense disambiguation that, when trained on unannotated English text, rivals the performance of supervised techniques that require time-consuming hand annotations. So just a reminder, this paper is quite old. It's from 1995. The algorithm is based on two powerful constraints that words tend to have one sense per discourse and one sense per collocation, exploited in an iterative bootstrapping procedure. Tested accuracy exceeds 96%. So this number really caught my eye. So before starting, let's just be clear about what these words mean. So a discourse is basically a discussion or a conversation. But what about a collocation? So collocation, a combination of words in a language that happen very often and more frequently than would happen by chance. So basically, some words occur li- together very often, and we all see these examples around us. So hello there, hello there. You might see these two words at the starting of many YouTube videos or uh, at the start of many messages. So this is something of that sort. So an introduction. The paper presents an unsupervised algorithm that can accurately disambiguate word senses in a large, completely untagged corpus. So note that the problem here is sense disambiguation. So assigning each instance of a word to establish sense definitions. This differs from sense induction, which uses distributional similarity to partition word instances into clusters that may have no relation to standard sense partitions. So basically, what they're saying is, suppose a word has multiple meanings, they want to distinguish what meaning is occurring in a particular sentence. So, say the word bank. Bank can be a river bank or a money bank. So, something of that sort. The algorithm avoids the need for costly hand-tag training data by exploiting two powerful properties of human language. So, if you've ever worked in annotating data, you might know how tedious it is. So, if this is preventing that then it can be a really great asset for any task. So one sense per collocation. So what they're saying is nearby words provide strong and consistent clues to the sense of a target word, conditional on relative distance, order, and syntactic relationship. So this is a pretty good point. What they're saying is the words which occur in the same sentence are more likely to have some like correlation or give clues about each other. Also, the farther apart they are, the less likely they are to help out in deciphering each other's meanings. But so this is where traditional RNNs also uh, fail in some sense because they are not able to preserve these long-ranging uh, dependencies. So, like an example of what I'm trying to say is, suppose someone says, "I am French and I like ABC and XYZ, and I also love to swim and tour and so on and so forth." And he writes a lot of stuff. And towards the end, he writes, "I generally speak in," and now you need to predict what word fits here. So nothing in this the vicinity of this blank words tells us what he speaks. This is all a part of the question. What gives us a clue is this word French here. So this person might be a French speaker because he's French. So this would be a reasonable guess in my opinion. So something of this sort is not being preserved here. Their assumption is that words like ABC and XYZ or I am French. So all of these would give information about each other. Also, the farther apart they are, or they are conditioned on some syntactic relationships, so you have some set rules which are being followed. Also, one sense per discourse, so the sense of a target word is highly consistent within any given document. So this is a much more fair, much more like valid assumption, I feel. So if someone is talking about I am at the bank and I am going to withdraw money from the bank. So here the both the banks are the monetary banks. Of course, the person could say post which I would visit the bank to do some fishing. And here the contexts are highly different. This bank is a river bank, but this bank is a money bank. But how often would you see such a sentence, right? So that is also a fair assumption. Moreover, language is highly redundant, so that the sense of a word is effectively overdetermined by 1 and 2 above. The algorithm uses these properties to incrementally identify collocations for target senses of a word given a few seed collocations for each sense. This procedure is robust and self-correcting and exhibits many strengths of supervised approaches, including sensitivity to word order information lost in earlier unsupervised algorithms. So just a note, here I use the traditional dictionary definition of collocation appearing in the same location, a juxtaposition of words. No idiomatic or non-compositional interpretation is applied. So this is exactly what we Googled, I guess. So they've just described their algorithm. So let's now dive deeper into their discussions on the individual properties. So the first property, which is in section 2, one sense per discourse. The observation that words strongly tend to exhibit only one sense in a given discourse or document was stated and quantified in Gale, Church, and Yarosky 1992. Yet to date, the full power of this property has not been exploited for sense disambiguation. The work reported here is the first to take advantage of this regularity in conjunction with separate models of local context for each word. Importantly, I do not use one sense per discourse as a hard constraint. It affects the classification probabilistically and can be overridden when local evidence is strong. So this is basically, suppose this what they're saying is, uh, enforcing something like that in this setting is not good, right? Because this bank has a different context. So the local setting, the word fishing here gives context about what this bank is implying. In this current work, the one cents per discourse hypothesis was tested on a set of 37,332 232 samples hand-tagged over a period of 3 years. The same data studied in the disambiguation experiments. For these words, the table below measures the claim's accuracy. So the claim's accuracy is when the word occurs more than once in a discourse. How often does it take on the majority sense for each discourse? And applicability. How often the word does more than once appear more than once in a discourse, right? So if a word plant is there, it has two senses: a living plant or a factory plant, so a nuclear power plant. What accuracy is implying is when the word occurs more than once, how often does it take on the majority sense for the discourse? So suppose you have a sentence and the sentence is dealing with plants. So suppose the majority, suppose, let me just give you an example of what I get they're trying to imply. So suppose you have the word plant say occurring, then you have some, right? So these are the different occurrences. So let's say this is occurrence number 1, this is occurrence number 2, this is occurrence number 3, and this is occurrence number 4. Now suppose this belongs to the sense that this is a nuclear power plant. So let me just call it a nuclear power plant. Nuclear power plant. This is also a nuclear power plant, but this is talking about the, say, the ecological aspects of a nuclear power plant, and this is talking about the biological plants, right? So the majority sense is a nuclear power plant. Now what they're trying to see is how often does it take the majority sense. So here it takes that sense 75% of the time, because you have three total four occurrences and three out of those are the majority occurrence. So 3 over 4, which is 0.75, so that is 75%. So their accuracy shows that when they're talking about, say, a living plant, if that is the majority sense, then 99.8% of the time that is the only sense which that word is using. And applicability is how often the word does occur more than once in a discourse. So, how often in the dataset that word occurs more than once in a discourse? Clearly, the claim holds with a very high reliability, so you can see the reliability is pretty high and may be confidently exploited as another source of evidence in sense tagging. So, what is sense tagging? Before that, let's just read this footnote. It is interesting to speculate on the reasons for this phenomenon. Most of the tendency is statistical. Two distinct arbitrary terms of moderate corpus frequency are quite unlikely to co occur in the same discourse, whether they are homographs or not. So, this also makes sense. You are unlikely to be talking about the river bank and the bank money bank at the same time. This is particularly true for content words which exhibit a bursty distribution. However, it appears that human writers also have some active tendency to avoid mixing senses within a discourse. Yeah, so you actively often try to avoid such things to avoid confusion for the reader. In a small study, homograph pairs were observed to co-occur roughly 5 times less than arbitrary word pairs of comparable frequency. Regardless of origin, this phenomenon is strong enough to be of significant practical use as an additional probabilistic disambiguation constraint. So I guess this was pretty clear from the examples that we saw already. Sense tagging, I guess, is just meant tagging uh, a particular occurrence is present in which sense. Now we have one sense per collocation, which we discussed here. The strong tendency for words to exhibit only one sense in a given collocation was observed and quantified in Yarowski 1993. This effect varies depending on the type of collocation. It is strongest for immediately adjacent collocations and weakens with distance. It is much stronger for words in a predicate argument relationship than for arbitrary associations at equivalent distance. Right. So if uh, exists a relationship between the words, so a predicate argument relationship, then it is much more likely to occur than suppose even if the predicate argument are some distance apart and you have another set of words which are some distance apart. This additional syntactic constraint also brings in some information, so it weakens with distance. We saw a counter example, but in general this is true in a lot of cases. It is very much stronger for collocations with content words than those with function words. So what are function words here? This latter effect is actually a continuous function conditional on the burstiness of a word, the tendency of a word to deviate from a constant Poisson distribution in the corpus, right? So let's just see what are function words. What are function words? A word whose purpose is to contribute to the syntax rather than the meaning, right? So it is all of these words. So I guess this also makes sense because content words being together gives us much more information than the words it is being together. So in excess of 97% for adjacent content words makes it an extremely useful property for sense disambiguation. A supervised algorithm based on this property is given in Yarowski 1994 using a decision list control structure based on Rivest 1987. This algorithm integrates a wide diversity of potential evidence sources, lemmas, inflected forms, parts of speech, and arbitrary word classes in a wide diversity of positional relationships, including local and distant collocations, trigram sequences, and predicate argument associations. So they've just mentioned previous works which have uh, used this property and what were they based on. The training procedure computes the word sense probability distribution for all such collocations and orders them by the log likelihood ratio of the prior of a given sense given the collocation divided by and taken, and a logarithm is taken. So as most ratios involve a zero for some observed values, smoothing is crucial. So the process employed here is sensitive to variables including the collocation distance, and the type of word and the expected amount of noise in the training data. So okay, so this is in a paper which was yet to appear at this time. By not combining probabilities, the decision list approach avoids the problematic complex modeling of statistical dependencies encountered in other frameworks. The algorithm is especially well suited for utilizing a large set of highly non-independent evidence such as found here. In general, the decision list algorithm is well suited for the task of sense disambiguation and will be used as a component of the unsupervised algorithm below. So they've just described uh, what the supervised algorithm was doing, and now they're basically establishing why these two properties make sense, and how now they're going to describe how it's being utilized in the unsupervised learning algorithm. So words not only tend to occur in collocations that reliably indicate their sense, they tend to occur in multiple such collocations. This provides a mechanism for bootstrapping a sense tagger. Okay, so if one begins with a small set of seed examples representative of two senses of a word, one can incrementally augment these seed examples with additional examples of each sense using a combination of the one sense per collocation and one sense per discourse tendencies. So basically, what they're saying is if you have just some training uh, uh, or some seed data which establishes okay these are the different senses and these are the different occurrences, then as you identify more words and disambiguate their senses, those new sentences can also act as examples. Although several algorithms can accomplish similar ends, the following approach has the advantage of simplicity and the ability to build on an existing supervised classification algorithm without modification. As shown empirically, it also exhibits considerable effectiveness. The algorithm will be illustrated by the disambiguation of 7,538 instances of the polysemous word plant in a previously untagged corpus. So I guess what polysemous means is multi-meaning, but I just need to be sure about the meaning. Yeah, the coexistence of multiple meanings. So let's just read the footnotes first. So this is the footnote for okay. So these are the other algorithms, variants of the EM algorithm, especially as applied by in this work, and okay, so they're now, I guess, describing which supervised algorithm it builds on without modification. So indeed, any supervised algorithm that returns probabilities with its classifications may potentially be used here. These include Bayesian classifiers and some implementation of neural nets, but not Brill rules. So I'm not sure what Brill rules are, but I guess I'll look that up later. So let's have a look at the step. So in a large corpus, identify all examples of the given polysemous word, storing their context as lines in an uh, in initially untagged training set. So okay, on the basis of the word plant, they've created this and they don't know the sense. So now step 2. For each possible sense of the word, identify a relatively small number of training examples representative of that sense. So let's have a look at the footnote first. For the purposes of exposition, I will assume a binary sense partition. It is straightforward to extend this to k senses using k sets of seeds. Okay, this makes sense. So what they're saying is, in the training data you've collected, manually identify the different sense disambiguations. In their case, they are assuming there are binary senses. So this can be accomplished by hand tagging a subset, but they will avoid this laborious procedure by identifying a small number of seed collocations representative of each sense and then tagging all training examples containing the seed collocates with the seed sense label. Alright. So what they're saying is they'll identify some group of words, a collocation of words which represents a particular sense. Then they look in the training samples and look for occurrences of that collocation, and using their assumption that a particular word is much more likely to appear in only one sense in a given discourse, they'll label some training samples. The remainder of the examples, which are typically 85 to 98%, constitute an untagged residue. So several strategies for identifying seeds that require minimal or no human participation are discussed in section 5. We'll go there later. In this example, below the words life and manufacturing are used as seed collocations for the two major sense of plants. So plant life and manufacturing plant together are creating the two senses, and then they have these sense words which do not fit in any of these, like uh, the manufacturing plant or plant life was not directly present. So uh, this part this partitions the training set into 82 samples of living plants, which is 1% of the data set, 106 examples of manufacturing plants, which is also all around 1% of the data set, and 7,350 residual examples, which comprise of 98% of the data set. So it is useful to visualize the process of seed development graphically. The following figure illustrates the sample initial state. Circled regions are the training examples that contain either an A or B seed collocate. The bulk of the sample points question mark constitute the untagged residue. So you can see you have some here and some here, and majority of it is untagged. So now step 3A, train the supervised classification algorithm on a particular sense seed sets. So basically either these or these, sense A or sense B. The decision list algorithm used here is the one from Yarosky 1994, which identifies other collocations that reliably partition the seed training data ranked by the purity of the distribution. So they'll look for particular phrases which are also present in these samples which have been labeled, which are characteristic or which are able to distinguish between the word senses. Below is an abbreviation of the decision list trained on the plant seed data. So their algorithm found that plant life is sense A, manufacturing plant is sense B. If the word life occurs within these many words, it is sense A. If the word manufacturing occurs within these many words, it is sense B. And log L is, I guess, the likelihood. A note. Note that a given collocate such as life may appear multiple times in the list in different collocational relationships, including left adjacent, right adjacent, co-occurrence at other positions in a plus minus k word window, and various other syntactic associations. Different positions often yield substantially different likelihood ratios, and in cases such as pesticide plant versus plant pesticide, indicate entirely different classifications. So I guess this also makes sense because the algorithm will look at all different configurations. So now let's have a look at step 3b. Apply the resulting classifier to the entire sample set. Take those members in the residual tagged as sense A or sense B with probabilities above a certain threshold. So you tell your classifier if you are 80% sure or 90% sure, then add that to that sense. So you have now effectively incremented your data, label data. Using the decision list algorithm, these additions will contain newly learned collocations such as species, microscopic animals, cell, and so on. That can reliably indicate the previously trained seed sets. The acquisitions of previous additional partitioning collocations from the co-occurrence with previously identified ones is illustrated in the lower portion of figure 2. So you can have a look at how it has been extended. Now you have step 3C. Optionally, the 1 cents per discourse constraint is then used to filter and augment this addition. The details of this process are discussed in section 7, so we'll have a look at that also. In brief, if several instances of the polysemous word in a discourse have already been assigned sense A, this sense tag may be extended to all examples in the discourse, conditional on the relative numbers and the probabilities associated with the tagged examples. So this is exactly what I was describing before. So now these newly tagged ones can also be leveraged. So you can see uh, labeling previously untagged context using the 1 cents per discourse property. So they're basically using the properties they've described to assign a sense to a particular collocation. This augmentation of the training data can often form a bridge to new collocations that may not otherwise co-occur in the same nearby context with previously identified collocations, such as bridge to the sense A collocate cell is illustrated graphically. So you can see there are bridges here. Similarly, the 1 cents per discourse constraint may also be used to correct erroneously labeled examples. Uh, if there are multiple senses and basically plant parts here occurs, so it might lead it might tell the classifier that this is indicative of sense B because plant parts might refer to the parts of a nuclear power plant, but this given the additional information that they got that uh, the sense for this discourse is biological, then they may conclude that this is a part of discourse sense A. And now you iterate over step 3, the training sets plus the newly added samples, and this will tend to grow while the residual will tend to shrink. Adding additional details aimed at correcting and avoiding misclassifications will be discussed in section 6. Alright. Step 4, stop when the training parameters are held constant, the algorithm will converge on a stable residual set. So there will be some examples which will not belong to either of these senses. Note that most training examples will exhibit multiple collocations indicative of the same sense. The decision list algorithm resolves any conflicts by using only the single most reliable piece of evidence, not a combination of all matching collocations. This circumvents many of the problems associated with non-independent evidence sources. Okay, let me just go over that again. The decision list algorithm resolves any conflicts by using only the single most reliable piece of evidence and not a combination of all of these. So this circumvents many of the problems associated with non-independent Evidence sources. So I guess this is referring to the fact that uh, occurrences of multiple collocations are not independent totally, right? They are dependent on each other, and if you directly try to uh, club together or sort of use the probabilities directly as independent probabilities, then that would lead to wrong results. So this is the final state, and you can see bridges and all being made. Step 5, the classification procedure learned from the final supervised training step may now be applied to new data and used to annotate the original untagged corpus with sense and probabilities. As abbreviated sample of the final decision list for plant is given below, note that the original seed words are no longer at the top of the list. They have been displaced by more broadly applicable collocations that better partition the newly learned classes. In cases where there are multiple seeds, it is even possible for an original seed for sense A to become an indicator for sense B if the collocate is more compatible with the second class. Thus, the noise introduced by few irrelevant or misleading seed words is not fatal. It may be corrected if the majority of the seed forms a coherent collocation space. So you can see it is no longer what we saw earlier, and these are not the seeds which we initially fed, but this is what the algorithm has learned. When this decision list is applied to a new test sentence, the loss of animal and plant species through extinction, the highest ranking collocation found in the target context species is used to classify as sense A, which is indeed present here, and which tells us that it belongs to sense A. So now let's have a look at options for training seeds. So the algorithm should begin with seed words that accurately and productively distinguish the possible senses. Such seed words can be selected by any of the following strategies. So use words in dictionary definitions. So extract seed words from a dictionary entry for the target sense. This can be done automatically using words that occur uh, with significantly greater frequency in the entry relative to the entire dictionary. Words in the entry appearing in the most reliable collocational relationships with a target word are given the most words weight based on the criteria given in Yarossi 1993. So seems like a pretty good approach. Look at the dictionary entry and see which words are occurring with uh, the word you're dealing with or the sense you're dealing with. Use a single defining collocate for each class. Remarkably good performance may be achieved by identifying a single defining collocate, so bird and machine for the word crane, and using these seeds for contexts containing one of these words. So WordNet is an automatic source for such defining terms. WordNet was used extensively for synonyms and stuff, and is still used uh, for low-level tasks, I believe, because at a high level, WordNet does not retain sense, I guess, in some sense, or uh, I'm not entirely sure, so I wouldn't be commenting further on this. But nowadays, deep learning models are de facto used everywhere. Also, label salient corpus collocates. Words that co-occur with the target word in unusually greater frequency, especially in certain collocational relationships, will tend to reliably be indicators of one of the target word senses. So, flock and bulldozer for crane. So a flock of crane is indeed bird representing bird, but bulldozer is more tending towards machines. You might argue, someone might say a flock of cranes sat on the large crane bulldozer, but that is some extreme case. A human judge must decide which one, but this can be done very quickly. So typically under 2 minutes for a full list of 30 to 60 such words. Co-occurrence analysis selects collocates that span the space with minimal overlap, optimizing the efforts of the human assistants. While not fully automatic, this approach yields rich and highly reliable sets with minimal work. So they've described three ways to get the initial set of seeds. Also, how do you escape from initial misclassifications? So, unlike many previous bootstrapping approaches, the present algorithm can escape from initial misclassifications. So, essentially, what they're trying to say is if you make some mistakes at the early stage, there are ways for you to make sure that they do not carry on to the later stages. Examples added to the growing seed set remain there only as long as the probability of their classification stays above the threshold. So if the classification begins to waver because new examples have discredited the crucial collocate, they are returned to the residual and may later be classified differently. So this is pretty interesting. So if the newer residuals are able, if the newly identified collocates dislodge some previously threshold crossing collocates, then they go back to the residuals. Thus, contexts that are added to the wrong seed set because of misleading words in a dictionary definition may be correctly reclassified as iterative training proceeds. The redundancy of language with respect to collocation makes the process primarily self-correcting. However, certain strong collocates may become entrenched as indicators for the wrong class. We discourage such behavior in the training algorithm by two techniques: incrementally increasing the width of the context window after intermediate convergence. So, the window of context which they allow is being incremented after some intermediate convergence, so which periodically adds new feature values to shake up the system, and randomly perturbing the class inclusion threshold similar to simulated annealing. So this threshold is also changed. Let's just be sure. Perturbing means changing. Right. So using the one cents per discourse property, the algorithm performs well using the local collocational information, treating each token of the target word independently. However, accuracy can be improved by also exploiting the fact that all occurrences of the word in a discourse are likely to exhibit the same sense. This property may be utilized in two places, either once at the end of step 4 after the algorithm has converged, or in step 3C after each iteration. At the end of step 4, this property is used for error correction. When a polysemous word such as plant occurs multiple times in a discourse, tokens that were tagged by algorithm with low confidence using local collocation information may be overridden by the dominant tag for the discourse. So now you know if there was some confusion whether which sense this should go to, the overall sense of the discourse might be dominant and tell you more information about which tag, which sense this collocation should go to. The probability differentials necessary for such a reclassification were determined empirically in an early pilot study. The variables in the decision are total number of occurrences of the word plant in the discourse, the number of occurrences assigned to a majority and minority sense for the discourse, and the cumulative score for both, so a sum of log likelihood ratios. So if cumulative evidence for the majority sense exceeds that of the minority by a threshold, the minority cases are relabeled. The case n is equals to does not admit much reclassification because it is unclear which sense is dominant. But for n greater than 4, so equal to 4, when more than 4 occurrences are there, all but the most confident local classifications tend to be overridden by the dominant tag. So by most confident local classifications, this might be something like I'll visit the bank to do some fishing. Uh, the use of this property after each iteration is similar to the final post hoc application, but helps prevent initially mistagged collocates from gaining a foothold. The major difference is that in discourses where there is substantial disagreement concerning which is the dominant sense, all instances in a discourse are returned to the residual rather than merely leaving the current tags unchanged. This helps improve the purity. So I guess this makes sense why all of this is being done. The fundamental limitation of this property's convergence is coverage. As noted in section 2, half of the examples occur in a discourse where there are no other instances of the same word to provide corroborating evidence for a sense or to protect against misclassification. So basically what they're saying is if you look at this table which we saw initially, you can see that in over 50% of the cases the word occurs only once. So you have to judge the sense by using only that word. So you are not getting additional information. There is additional hope for these cases. However, as such isolated tokens tend to strongly favor a particular sense, we are yet to use this additional information. Alright. So evaluation, the words used in these evaluations were randomly selected from those previously studied in literature. They include words where sense differences are realized as difference in French translation and drug and duty, a verb poach, and words used in Schutz 1992 disambiguation experiment, tank, space, motion, and plant. The number of words studied has been limited here by the highly time consuming constraint that full hand tagging is necessary for direct comparison with supervised training. So basically what they're saying is if you want to directly compare with supervised training, you need to do full hand tagging, which takes time. So then this process will be very time consuming. The data were extracted from 460 million word corpus containing news articles, scientific abstracts, spoken transcript, all this stuff. Column 6 to 8 illustrate differences in seed training option. Using only two words as seed does surprisingly well. Alright, 90.6%. Then you have using a dictionary definition or using the top collocations. This approach is at least successful for senses with a complex concept space which cannot be adequately represented by single words. Using the salient words of a dictionary definition as seeds increases the coverage of the content space, improving accuracy to 94.8%. However, spurious words in example sentences can be a source of noise. Quick hand tagging of a list of algorithmically identified salient collocates appears to be worthy the effort due to the increased accuracy 95.5% and minimal cost. So they mentioned how short of how much less time it takes to like do this process. Columns 9 and 10 illustrate the effect of adding the probabilistic one sense per discourse constraint to collocation based models using dictionary entries as training seeds. Column 9 shows its effectiveness as a post hoc constraint. Although apparently small in absolute terms, on average, this represents a 27% reduction in error rate. When applied at each iteration, this process reduces the training noise, yields the optimal observed accuracy in column 10, and for comparative performance of column 5, it shows the relative performance of supervised training using the decision list algorithm applied to the same data and not using any discourse information. And supervised training uses the additional 1 cents per discourse constraint frequently, exceeds this value. So they are able to beat the supervised model. Column 11 shows the performance of Schutz unsupervised algorithm applied to some of the words trained on New York Times news service corpus. Our algorithm exceeds the accuracy on each word with an average relative performance of 97% versus 92%. So they're able to beat it by on average 5%. The maximum possible error reduction is 50.1. The difference is even more striking given Schutz data exhibits a higher baseline probability for these words and hence constitute an easier task. Right. So these are the words, these are the sample sizes, these are the accuracies achieved, and these are uh, the ones which use algorithm. And this is when you use 1 cents per disambiguation at end only or at each iteration. So this is a pretty easy to go through table, and it gives a lot of information also. Now let's have a look at the comparison with previous work. This algorithm exhibits a fundamental advantage over supervised learning algorithms, all of these, as it does not require costly hand-tag training sets. It thrives on raw, unannotated monolingual corpora, the more the merrier. Although there is hope from using aligned bilingual corpora as training data for supervised algorithms, this approach suffers from both limited availability of such corpora and the frequent failing of bilingual translation differences to model monolingual sense differences. The use of dictionary definitions as an optional seed for the unsupervised algorithm stems from a long history of dictionary-based approaches, including Lesk, Luthri, Veronin, and Aiden Slater. I'm really sorry if I mispronounce any of those names. Although these earlier approaches have used often sophisticated measures of overlap with dictionary definitions, they have not realized the potential for combining the relatively limited seed information in such definitions with the nearly unlimited co-occurrence information extracted from text corpora. Other unsupervised methods have shown great promise. Dagan and Itai 1994 have proposed a method using co-occurrence statistics in independent monolingual corpora of two languages to guide lexical choice in machine translation. Translation of a Hebrew verb object pair such as latom and Jose is determined using the most probable combination of words in an English monolingual corpora. This work shows that leveraging bilingual lexicons and monolingual language models can overcome the need for aligned bilingual corpora. Hurst 1991 proposed an early application of bootstrapping to augment training sets for supervised sense tagger. She trained her fully supervised algorithm on hand labeled sentences, applied the results to new data, and added the most confident tagged examples to the training set. Regrettably, this algorithm was only described in two sentences and not developed further. Our current work differs by eliminating the need for hand labeled data and by joint use of collocation and discourse constraints. Schultz 1992 has pioneered in the hierarchical clustering of word senses. In his disambiguation experiments, Schultz used post hoc alignment of clusters to word senses. Because the top level cluster partitions based purely on distributional information do not necessarily align with standard class sense distinctions. He generated up to 10 sense clusters and manually assigned each to a fixed sense label. In contrast, our algorithm uses automatically acquired seeds to tie the sense partitions to the desired standard at the beginning, where it can be most useful as an anchor and guide. In addition, Schultz performs his classification by ordering documents as a large unordered bag of words. By doing so, he loses the important distinctions such as collocational distance, word sequence, and existence of predicate argument relationships. In contrast, the algorithm which is being used in this paper uh, uses these properties carefully, adding considerable discriminating power lost in relative impoverished models of language. Now, so this paper was pretty good, pretty easy to understand, and pretty uh, novel, I believe, for that time, and still all the points seem pretty valid and the assumptions seem pretty sound. In essence, our algorithm works by harnessing several powerful empirically observed properties of language, namely the strong tendency of words to exhibit only one sense per collocation and per discourse. It attempts to derive maximal leverage from these properties by modeling a rich diversity of collocational relationships. It thus uses more discriminating information than available to algorithms, treating documents as bag of words, ignoring relative positions and sequence. Indeed, one of the strengths of the work is that it is sensitive to a wider range of language detail than typically captured in statistical sense disambiguation algorithms, which we saw earlier. Also, for an unsupervised algorithm, it works surprisingly well, directly outperforming Schultz's unsupervised algorithm on a test of the same four words. More impressively, it achieves nearly the same performance as the supervised algorithm given identical training context, and in some cases, superior performance as well. This would indicate that the cost of large sense tag training corpus may not be necessary to achieve accurate word sense disambiguations. And now they've also thanked the author, thanked the supporters. So overall, this was a pretty great read, and sorry for being away for a long time. I'll probably upload a few videos in quick succession now. So thank you guys for joining in. If you have any suggestions, please comment down below, and do like, share, and subscribe. And hope to see you guys again.